Hey AP Statistics. In this part 2 video of 8.3, we're going to put it all together. We're going to do the state plan do conclude for confidence intervals for mu. So state, these are going to look identical to what we've done before, only we're going to be doing it for confidence intervals for mu now instead of p. State the parameter you want to estimate and the confidence level. Then there's the plan step where you identify the appropriate inference method. Now we've added a new method. We've got the one proportion z interval from section 8.2. In this chapter, in this section, we're going to be doing our one sample t interval for mu. Technically, there's also z interval if you, for whatever reason, know sigma. That one kind of exists. It will never really do it, but it's really most often the one sample t interval for mu. And then do, if the conditions are met, perform calculations, then you do the math, and then you interpret yours in context. So let's go on through one of these. In the previous section, you learned about the American adults that claim to have read a book in the previous 12 months. This was based on a 2016 Pew Research study, Center study that interviewed a random sample of 1,520 American adults. The same study also reported the average number of books read by members of the sample, including those who reported reading 0 books. And so X bar was 12 books with a standard deviation of 18. So construct and interpret a 95% confidence interval for the mean number of books read by all Americans in the previous 12 months. And then after that, in 2011, they reported that adults read on average 14 books with the previous 12 months. Does your interval from part A provide evidence to think that the mean is different from 14? So we'll answer that after we construct the interval, which is going to be this long process where we go through state, plan, do, conclude. So let's construct it. State step. We're going to do a 95% confidence interval for mu, where we define the parameter. So we state that our what our confidence level is and what procedure and what parameter we're going to be estimating. So the true mean number of books read by all American adults in the previous 12 months. Then we move on to plan, which is where we state the type of procedure we're going to do, which in this case is a one sample t interval for mu. One sample t interval, since we don't actually know sigma, we use t, and for mu, the population mean. And then we need to check our 3 conditions. Our random condition, we have a random sample of 1,520 American adults. The 10% condition, there are far more than, that's less than 10% of the population. There are far more than, would that be 15,000 American adults. And then the normality condition. In this case, our sample size is quite large, regardless of the shape. It sounds like there's a whole bunch of people who are reading 0 books, so the shape is not normal for our population, but central limit theorem, sample size is large enough, so we can go ahead and proceed. So that's our state step and our plan step. Then we move on to do and actually calculate this. So we get our X bar. And so this one is screwed up, but this is actually right. This is the X bar, sample mean 12 plus or minus 95% confidence. So this was based on a degrees of freedom of, what was our degrees of freedom? 15, 19. Basically, it's a normal distribution. Notice that 1.96 there. That's effectively a normal distribution since that degrees of freedom is so large. And then we use the sample standard deviation of 18 over that square root of 1520. Basically, there's no additional error from using that sample standard deviation in place of sigma because it's just such a large sample. It should be extremely close to it, and this should cause very little additional error. And then we can calculate that into our margin of error and get our range of values. And we're not done. We've done it, but we need to conclude. And sorry, ignore pretty much this line up here. They did use degrees of freedom 1,000 from the table, but really the degrees of freedom was 1519 to get that t star, and the inverse t of 0.025 to get that value with that degrees of freedom. Conclude, we are 95% confident that the interval from 11.09 books, notice that this has units now, to 12.91 books captures mu, the true mean number of books read by all American adults in the previous 12 months. So we are 95% confident that that interval contains the actual mean number of books read. So then part B is in a 2011 Pew Research reported that American adults read on average 14 books in the previous 12 months. Does your interval from Part A provide convincing evidence that the 2016 mean is different than 2014? Has it gone up or down maybe? You know, is it no longer 14? Well, our interval, just to remind you, went from 11 to 12.9. 14 is not in that interval, so we're pretty confident it doesn't include, it's 14. It's not considered a plausible value. So yes, we do have convincing evidence that it has changed. 14 is not in that confidence interval. It's not plausible value for the mean number of books read by all American adults in the previous 12 months. All right, another problem here. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electronic device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings for a random sample of 20 screens from a single day production. So they've got us our raw data there. Construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. And so this is our random sample of 20. We're going to do the full process again. I'm going to kind of fly through it because I just point out the differences. So we need to state we are going to do a 90% confidence interval for mu, the mean tension of all the screens that day. Then our plan step. This is still a one sample t interval for mu. We've got random sample of 20. Our 10% condition, we're going to assume that 20 is less than 10% of all video terminals produced that way. The really interesting step that's different here is the normality step. They don't tell us that the population's normal. They don't tell us that we don't have a large enough sample size to be able to ignore it. So with this smaller sample size, we want to graph this. What we want to see is that there's not strong skew or outliers, that it's somewhat symmetric. Again, it doesn't have to be perfectly symmetric or anything. Just there's maybe a slight skew, nothing too strong. And this looks fine. The dot plot does not show strong skewness or outliers, and so we can proceed and know that T procedures are appropriate. So then we actually do, this part's pretty much the same. There's those numbers, the actual mean and standard deviation. And so then we use that as our point estimate. Our degrees of freedom is 19, so we can find the t-star either using the table or the calculator. And that's how many standard deviations we're going to go, standard errors really. 36.21 is our sample standard deviation, which you can get by typing both of those numbers in. You can type in all 20 numbers and do one variable stats to get those. And so we end up getting our confidence interval from 292 to 320. And interpreting that, we are 90% confident that the interval from 292 to 320 captures the true mean tension of the entire batch of video terminals produced that day. Note, it is not enough just to make a graph of the data on your calculator when assessing a normality. You can't just say, I looked at my calculator. You have to actually sketch that graph on your paper to receive credit, to show, like, yeah, here it is. It doesn't have a strong skew or outliers. Just any one appropriate graph. A lot of times the easiest one to draw is a box and whisker plot. It's just, you know, the box and the whiskers. It's pretty easy. But showing a graph will sometimes be a requirement. Choosing a sample size. We did this for proportions. We're going to do this here. A wise user of statistics never plans data collection without thinking about analysis at the same time. You can arrange to have both high confidence and small margin of error by taking enough observations. If you have enough money and time to do that, that's going to generally be best to shrink that margin of error. So we can solve a similar formula to last time. We're going to have a margin of error that we want to figure out, and we can figure out what t-star is, but and estimate, like, there's a few problems that show up here. So then we want to solve for n, but like t-star depends on n, right? So we don't know, I guess I'm doing this out of order. So the sample standard deviation we don't have yet because we haven't taken our sample yet. And then the t-star also depends on the sample size that we choose, so that it depends on the degrees of freedom. So what you should probably do in this case, you may be able to get some estimates for those things. You can actually just use the z interval one, and you have to have some standard deviation to begin with. They're going to have to give you a standard deviation that we know, and then you're going to be able to plug in a z star that corresponds to that doesn't rely on degrees of freedom, and you can do this type of formula to solve for your sample size. And so we kind of, it's just not ideal, but you should be able to get approximate with it. You could always kind of round up a little bit to be sure that your margin of error is within the threshold of what you're desiring. So Determine the sample size n that will yield a C% confidence interval for a population mean with a specified margin of error. First of all, you need to get a reasonable value for a population standard deviation S from an earlier or pilot study, so use that for the numerator. Find a critical value Z star from the standard normal curve, and then set the expression for the margin of error to be less than or equal to that margin of error, and solve for n, solve for that denominator. So quick example of that. Researchers would like to estimate the mean cholesterol level M of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter. So that's our margin of error that we want to be within of the true value of M. And we're going to do it at 95% confidence. A previous study involving this variety of monkeys suggested the standard deviation of cholesterol is about 5 milligrams. So they've got to give you some sort of previous study or known sigma to be able to calculate that. What's the minimum number of monkeys the researchers will need to get satisfactory estimates to be within 1 milligram of the actual population cholesterol level, mean cholesterol level? And so 95%, we're going to just go with the Z star for that, which is 1.96. We've got 5 is our sigma that's known, and is what we're figuring out when it'd be less than 1. And so you just set up and solve the algebra here. So we can multiply by square root of n on the other side. This one works out pretty nice because there's nothing then to divide. It's just n over there, and we can square both sides. And we get n has got to be greater than or equal to 96.04. And once again, we got to go up to the next whole number. So to be sure that we're less than 1%, we actually have to go up to 97. And so the researchers would need at least 97 monkeys to estimate the cholesterol levels to their satisfaction. That is within 1 milligram of the actual mean. So we can be 95% certain of that. Another caution, although we assumed a value for the population standard deviation sigma to calculate the required sample size, you should not assume a value for sigma when calculating a confidence interval for mu.